Getting wired for wireless. In order to have high-performance Wi-Fi, it's essential to have sufficient performance in the switching underlay. The wired infrastructure needs to provide adequate speed for connections to the switch, for example from the access point, as well as the uplinks to aggregation and core switches and to the cloud. Network performance is only as fast as the weakest link. Having really fast access points is great, but if the underlying network can't keep up, then you won't get the full value from it. Or if the internet connection can't handle the aggregate throughput from all of the users and devices, you have the same problem. In an ideal network, all of the components are well matched to handle the network traffic. At any point in the connection between a user and the data center or cloud, a bottleneck will slow application performance. So let's follow the data flow starting from the user or device. The first step for the wired network is the connection from the AP to the switch. Today, the overwhelming majority of enterprise-class switches have 1 gigabit access ports. Up through 802.11n Wi-Fi, the total throughput possible through a wireless access point was below 1 gigabit per second, so connecting a switch to the 1 gig port was adequate. Anything faster wouldn't make any difference to performance. The AP was the limiting factor to performance. With the advent of 802.11ac and then 802.11ac Wave 2, the AP has the potential of more than a gigabit per second throughput. And if you can read the fine print there, according to the Del Oro report, almost all APs sold as of 2017 were 802.11ac. Therefore, a 1 gigabit access port could now possibly be the bottleneck to top performance. With prior generations of Wi-Fi, 802.11a, b, g, and n, the APs could only support up to about 600 meg, though practically they couldn't process more than 200 to 300 megabits per second throughput. So a 1 gig access port could handle all the data that the AP could push out. With 802.11ac Wave 1 or the more recent Wave 2, an access point is capable of up to 2.3 gigabits per second, though the practical limit is a little bit less. Our lab tests have been able to generate around 1.5 gigabits per second. So you might consider a 2.5 gigabit port to avoid the access port from being a bottleneck. Higher speeds won't provide any greater performance for Wi-Fi. The next generation 802.11ax APs are expected to begin shipping in the latter half of 2018, although the IEEE standard is not expected to be ratified until 2019. Theoretically, the chips will support almost 10 gigabits per second. It's too early to know, but practical limits are likely to be much less. From what I've heard, most 802.11ac APs will have 5 gigabit ports, not 10. Suffice it to say that to eliminate possible bottlenecks, you'll want to consider 1, 2.5, or 5 gigabit Ethernet ports on your access switches for access points. For most other devices, such as desktops, printers, voice-over IP phones, etc., they'll connect over 1 gig ports. There are a few devices coming, such as some high-end Mac workstations that will have 2.5 gigabit ports, but they're an exception. You'll also need to consider uplinks. Access switches had, and many still have, 1 gig uplinks. We're seeing more customers moving to 10 gigabit uplinks, with more and more looking at 40 gig and 100 gig uplinks. You'll need to consider not only the uplink speeds, but also the number of uplink ports. For example, the base ICX 7150 switches have up to 4 10 gigabit uplinks, while the ICX 7150Z series and the ICX 7250 switches have up to 8 by 10 gigabit uplinks. You'll want to make sure that if you total up all the inputs to the access ports, you want to be able to push that amount of data up to the core. Otherwise, you get oversubscription. More data coming in that can go out, or vice versa. That can cause delays to applications, giving you that little spinning image waiting for a response. And similarly, you want to move up to the aggregation and core of your network. Make sure you don't have potential bottlenecks anywhere in your network. Ruckus Networks leads the way in switch performance to provide optimized Wi-Fi performance. Ruckus ICX switches have a long history of innovation. The fast iron switch operating system, which today is still what drives the Ruckus ICX switches, was originally developed by Foundry Networks over 20 years ago. Foundry was a switch industry leader with the first 1 gigabit switches and then again with the first 10 gigabit switches. Brocade acquired Foundry Networks in 2009 and continued that legacy for performance, introducing the first 40 gig campus switch to the closet. Brocade was the first and still the only vendor to deliver PoE switches with 90 watts per port with the ICX campus switches. That tradition continues now as part of Ruckus Networks, acquired by Eris in 2017, delivering the first campus stackable switch with 100 gigabit links. Ruckus Networks continues the legacy of high-performance switching solutions. From small, compact, fanless switches ideal for out-of-closet uses such as in classrooms or offices, to high-performance stackables for use in wiring closets, as well as aggregation and campus core or data center switches. Ruckus Networks offers the most flexible connection options, ranging from enterprise-class gigabit connectivity to affordable 2.5 gig multi-gigabit connections in an entry-level switch that offers industry-leading value for the money, to top-of-the-line performance with 1, 2.5, 5, and 10 gigabit connections, to meet the most demanding performance requirements for access devices and wireless access points. In each class, switch for switch, Ruckus offers more and faster uplinks than competitive options. We're the only vendor that offers 100 gigabit links in a stackable access switch with no oversubscription. Ruckus delivers unbeatable performance and options that complement even the highest density Wi-Fi deployments. Thank you. Please continue to the next video in this series or go to www.ruckuswireless.com for more information.